So today I will continue talking about statistical mechanics and the role of statistical mechanics in quantum mechanical description. And the example today I will talk about is so-called photon gas. So if you remember in the Blackbody radiation, we had a distribution, energy distribution, and the way from the effort to explain it, the quantum mechanics emerged. And at the time I promised you we were going to explain how Planck came up with his formula, and hopefully today I'll show you that. And for that we are going to consider radiation in a cavity like a gas, right? Exactly like the gas we considered last time, we are considering a photon gas, and this photon gas is different from like the usual gas in different ways. First of all, it doesn't have a mass, right? And its energy is different, but also like in a classical gas, the atoms or molecules inside the gas is conserved, whereas in a photon gas, the cavity walls can create photons, or they can absorb photons. The number of photons inside the cavity is not conserved. So let's consider that. First we need to come up with an equation for number of states. And if you remember, we were thinking about some three-dimensional box, each with linear dimension L, and L. And we said that the quantization, so we have to fit the electromagnetic wave inside the box, and the amplitude of the wave has to vanish in the walls in each direction. And for this to happen, we said we need to have let me use a different integer because there will be many integers in this case, like some jx, which is an integer, should be equal to L, right? So this is integer. So this is the way we fit a wave in the x direction, but we can also repeat the same thing for y and z directions. So let me push that a little bit. Right, for each direction I have to have the different integer. So this one let me call it jy, this one let me call it jz. Here, these are all positive integers. But in real world, we don't have like a cube of cavity, right? We have like some arbitrary shape, like maybe like a more like round shape. And for that, we can look in like an arbitrary direction, and in that arbitrary direction, I have to fit the wave. Not only the shape changes, but also the direction I'm considering is going to change. And for that, I'm going to define like a j, which is formed from this jx squared plus jy squared plus jz squared, right? So now this can be in any direction. By adjusting jx, jy, jz, you can get j in any direction. And the quantization condition will be lambda over 2 times j should be linear dimension. Like if it is like a spherical container, it's going to be L in any direction, which is going to be the diameter of the container. Now we need to determine number of states, and number of states is determined from geometry, like so. So let me just give you the picture in like 2D. In 3D you can generalize it. So suppose this is jx and this is jy, and in each direction I have many dots, right? So these integers, and there's like many dots here, something like that. I don't know if you can see these dots. Yes, you can see it. And we can just duplicate and duplicate, something like that, right? Maybe the dots are supposed to be in the limit of jx and jy go to infinity. The spacing between the dots is actually much smaller, but for demonstration purposes, I exaggerated a little bit. And there's also jz, which is not drawn. But for this general direction, we are thinking about like a direction like this. Suppose this is my j, right? And so as long as the length of j is unchanged, I can take it in any direction, and it's going to be given with the same condition, right? And for this to happen, I need to consider, maybe I can take a little smaller, because I'm not going to be able to fit it here. So all these j's in that circle are going to have the same quantization condition. And now I need to find the number of states, how many dots I can put inside a little bit like a tiny dj inside. Okay, is that clear? So that's what I'm going to calculate. And this is calculated from the geometry. Let's write this. The number of states, j dj, this means the number of states between j and j plus dj. So this is number of states. Okay. First, in this two-dimensional drawing, I need to have like 1/4 of the entire plane, because I only allow positive jx and jy. In the three-dimensional case, I have to divide it by 1/8, right? There are like 8 quadrants. And times the volume inside this shell is just the area of this shell times the thickness, and the volume is like 4 pi j square times, and the thickness is dj. But since photons can have also polarization, which is not given with the simplified picture, we know they have it. So I'm also going to multiply with 2. So this 2 is polarization. Kind of like a spin, but for photon. But this is not what I want. I want to convert this to like my variable is not j. My variable is either frequency or wavelength, and either one is fine, and they are connected by like this usual formula: c is equal to lambda times nu. Okay, so how do I convert this? Okay, here is my j. So this condition. So j is equal to then 2L divided by lambda. So this is j, and 1 over lambda is equal to mu over c. So this is going to be 2L over c times mu. Did I get it right? 2L over c mu. Okay, good. And I can also do this dj. I take the derivative on both sides, and this is 2L divided by c times d mu. Then I'm going to just write these things. So this is 2, actually let me write everything. So j square is going to be replaced with 4L square divided by c square times nu squared, and dj is going to be replaced with this, right? And if I collect everything, let me just clean this up. So this one, and this one will cancel, and I have here 4, so this is like 8 pi, and I am going to have L square and L cube. I want to shorten it by calling it volume. So this is volume divided by c cube. I think I absorbed all the coefficients. this. And I have nu squared d nu. If this left-hand side is the number of states between j and dj, I'm going to define this to be a number of states between nu and d nu. But also, your book defines this capital G of nu, which is number of states per unit volume, and it is going to be just exactly the same thing without v. Let me just copy that and just erase this. So this is 8 pi. So number of states per unit volume. I just divided G by volume to get that. Okay, now I got G, the second thing. So in the statistical description we introduced on Monday, what was the second thing we needed? So we have G, but we also needed one more thing. Right, distribution function. But before the distribution function, let's consider classical case. Case 1. Suppose we didn't know anything about quantum mechanics, and we said like exactly like Rayleigh jeans. We said, okay, photon, maybe it is kind of like a classical gas, and consider like a classical energy per state. So what is the classically average energy per state at a given temperature? So at T, from the equipartition theorem. Yes, exactly. So this E bar is going to be equal to, so this is energy per each photon if you want. I'm going to put like, if you want, it was number of degrees of freedom times 1/2 kBT. But because we know photon is like has two polarization, I'm going to include these two here. But actually, just a historical note, Rayleigh jeans and later also Planck, they were not thinking about that. They were thinking about like these vibrators on the walls of the container, but it gives exactly the same thing. Then let's write this. Energy per volume in region nu to nu plus d nu. If you remember, we had to write ugly equations with long text like this when we were first introducing blackbody radiation, and it is going to be average energy times number of states. Right? That's all we need, nothing else. Then for this side, we said this is, we use little u of v d nu for this. So we said energy per volume in nu to nu plus d nu, which is shown by u of nu d nu is equal to, okay, this E bar is going to be, okay, let me just write all of these things. This is 8. I think this is supposed to be pi cube, right? Or maybe not pi cube. This is 8 pi. So this is c cube. And this is kT coming from this E bar. And this is nu square d nu. And this nu square d nu comes from here. And this is what we called Rayleigh jeans. And later, okay, this is now we know how they wrote it. They just wrote it exactly what we know at this moment. And now let's also remember what the problem was with this. So if you look at u as a function of frequency in the blackbody radiation, what we see was like at small frequency it was like almost 0. It was increasing to a peak, but at some point it was also going to decrease like this. So this is experiment, blackbody radiation. And if you plot this, right, this is like kT is some constant, nu square, right? If you draw it, it's going to be something like that. So this is Rayleigh-Jeans result. Now, typically people just present this like, oh, this is kind of like a failure, but it's actually not a failure. It's like a big step, because first you are taking like a radiation, which is like a completely different kind of beast, and you say that you can actually apply the laws of statistical mechanics to this, right? That's not an easy step forward. But they got the wrong result, that's still fine. But even though it is wrong, at low frequencies, it is still pretty good, right? And this is what we call like later UV catastrophe, because at high frequencies, it's just going to blow up. Another thing is like if you integrate the whole spectrum, if you integrate d nu from 0 to infinity, this is which is the total power from coming from the blackbody radiation at all frequencies, u nu. This is supposed to be finite. We are going to come to another law for this in a little bit, but Rayleigh-Jeans result does not have that either. So this was case 1. If we take a photon to be like a classical object, now let's consider photon to be a quantum object. Case 2, like a quantum approach, and use what Planck derived. So if you remember what Planck was saying, that again the vibrators in the walls of the cavity are quantized, and it was Einstein to suggest it was actually not vibrators but the photon itself quantized. But let's say what Planck said, and the energy of this quantization was given by some constant, which is later named for Planck. This is like h nu, but there can be like different quantas, and we call it like n times h nu. So Planck first write this, and then used Maxwell-Boltzmann distribution. Probability, which is what is, according to Maxwell-Boltzmann, what is the probability to have this energy at temperature T? We talked about this last time. It was like a simple function. E to the minus energy divided by kT, right? So this is En divided by kT. So if this is the probability, how we find average is we first sum over all possibilities, we multiply that possibility with probability, and we have the number of photons, and we normalize with total probability, right? So this is for normalization. That's usual formula from probability. And this can be calculated. So this is sum over all n epsilon of n e to the minus beta epsilon of n, and divide the entire thing with e to the minus beta epsilon of n. And I use beta to shorten 1 over kBt here. Now we need to find like if, okay, here n goes from 0 to infinity, n goes from 0 to infinity, and all of them. So need to sum this series. So let x be equal to beta times h nu. Then the series we need to sum is like this. So let's first sum the simplest one, the denominator, and it's going to be n is equal to 0 to infinity e to the minus x to the n, right? That's exactly rewrite of this. I just defined an x to write in a shorter space. Good. And what is the result of this sum? I think everybody knows this summation formula. So if you have something like 1 plus u squared plus u cubed plus u to the fourth What is the result? 1 over 1 minus u, but u in this case is e to the minus x, right? So I can clean that. And let's now put back what x is. This is 1 over 1 minus e to the minus beta h nu. Now I also need to sum this for a series. Let me just copy this. Not only this, but I also have, you can see n here, right? I think this is not n, this is h nu, n times h nu. N times h nu, because each energy is this. I'm trying to average. Okay, this side is correct. So this is n times h nu. H nu is going to come out, so this is going to be something like, let's write it, h nu, and this is something like that. How do I sum this? Yeah, maybe I can show you the trick and you can hopefully remember the next time. So this is minus beta. Actually, let me write it like this is minus beta En. So this is En, and I can write this thing as like a derivative, right? If I take the derivative with respect to beta of this series, it's going to give me, I'll just take the derivative of each term, and it is going to be n is equal to 0 to infinity, e to the minus beta e of n, and there will be minus En, but if I put the minus here, I don't need to put it here. Then I can just sum this series and take the derivative, but this series we just summed, so this is going to be this thing, and we need to take minus del beta, and this is going to be like a simple derivative, minus 1 over 1 minus e to the minus beta h nu minus e to the minus beta h nu and minus h nu, right? And yeah, now I have, okay, this sum divided by this sum, so let's just put everything together. So average energy is going to be equal to, so this entire thing and divided by this thing. So I'll cancel this one. No, I'm not going to cancel that one. So I think I forgot to square this, right? There's like a, like when I take the derivative, there's like minus 1, there's like a square, okay. And there's, I think now this is correct, so this is going to be square. Now with one of them, I'm going to cancel this. And,
In the line where you took minus the derivative of the sum, shouldn't that give us n starting from 1 and a negative?
This line?
Yeah, in the right side.
This side.
Yeah. Shouldn't we start from n equal to 1?
But it is inside, right? Like En is, you can include En is equal to 0, but it is 0 anyways. Right? Yeah.
But shouldn't we start the sum from 1?
So sum can go, like there is no difference between sum starting from 0 and sum starting from 1, right? Because n is equal to 0, it's going to be 0 anyways. Because this is En is n h nu, even if you start from n is equal to 0, it doesn't change. That's why I put it like, okay. Oh, also like there is this, I think, extra minus that I need to include. So there are in total 1, 2, 3, 4 minuses. And this E bar is going to turn out to be e to the beta h nu divided by 1 minus e to the minus beta h nu times h nu. And if I multiply both numerator and denominator with e to the beta h nu, so this one is going to be e to the, I think this one is minus, right? I am multiplying both numerator and denominator with e to the plus beta h nu. This is going to be beta h nu. This is going to be 1. This is going to be 1. Is that clear? And this is E bar. And it turns out, if you remember, E n was equal to n times h nu, and E bar is average n times h nu, and average n of nu is 1 over e to the beta h nu minus 1, which is exactly Bose-Einstein distribution with e to the alpha being 1. And we said for photons, alpha was going to be 0 anyways. Okay, I think this, like, just to make the notation consistent, we call this one F in our earlier discussion. Okay? Any questions or comments? And lastly, now we can write this U of nu, d nu is going to be equal to this first number of states. Number of states is going to be 8 pi over c cube nu squared, right? And energy of each state is going to be h nu divided by e to the beta h nu minus 1 and d nu. And this is exactly what we called Planck's radiation formula. So this is Planck's formula. And we know this formula fits exactly with this experimental line as long as you choose h to be Planck's constant. Good. Any questions or comments? So just a couple of comments. There are a couple of flaws, but hopefully you appreciate these mistakes these big people made. This is also wrong, right? First of all, what is quantized is not the walls of the cavity. What is quantized is, because if vibrators in the walls were quantized, we didn't have En is equal to n h nu, right? We also have like n plus a half. There is this 0 point energy, right? That's a mistake. And if you include this 0 point energy, you are not going to find this formula. So that's the first thing. And the second thing is, what is quantized is the photon itself. Photon itself is, and the photon is actually described with what we actually calculated. Photon itself is quantized. And this is due to Einstein. In my opinion, it's one of his biggest contributions. And this is how he explained the photoelectric effect, right? Somehow Einstein's E is equal to mc square is more appreciated, but actually with E is equal to h nu, he introduced like a much bigger change, right? Which is the quantum physics itself. But all of these mistakes can be fixed, and the way to fix them is like just go to the introduce like multiplicity and talk about entropy and all of these things, which you will do in another course. But the result will be like this. Good. Any questions or comments? So now let's let's calculate number of photons in cavity, exactly like we calculate number of atoms in a container to find the arbitrary constant. So for this case, we don't have any arbitrary constants. Let's write the entire thing. So this is N over V is equal to, if you sum over all states with all particles, right? E nu, G nu, and F Bose-Einstein of nu. So this, right? Find all energies, and at all energies, all particles, and sum everything up, you should get the total number of photons. And this thing is going to be equal to, let me write 8 pi over c cube in front. So this is from 0 to infinity. So this is d nu, this is nu squared, 1 over e to the h nu over kt minus 1. And I do exactly the same way to put this integral in dimensionless form. So there's like h nu over kt. I'm going to put h over kt here and h over kt here, and I'm going to have kt over h cubed. Is that right? Yes. And I will write this as like 8 pi over c cube kt over h cube, and this integral from 0 to infinity. Now this is like a dimensionless integral, the u squared 1 over e to the u minus 1. And you can just put this a constant, or if you have Mathematica, you can put this in Mathematica, but the result is so-called Riemann zeta function. This is 2 times zeta 3, and its numerical value is like something like 2.4411. Right? Then n over v is going to be equal to 8 pi over c cube 2 zeta 3 kt over h cube. Okay. Even though we are treating things like a gas in a container, you can see the number of photons is changing with temperature. It's completely different from like a classical gas. The number of a classical gas is fixed, but as you increase the temperature, you are going to have more and more photons in a cavity. Why did we say?
We say that it's equal to n over v, but
right, if you like sum over all particles, right, this is, so you are summing over all states, right, this is the nu, and g nu is going to be density of each frequency, and you are also counting how many photons you have in each frequency. Sum over all frequencies and multiply it with average number of photons in each frequency. This is going to be total number of photons. Okay, like one more step, and let's take a break after that. Let's also, okay, we calculate total number. Now let's calculate the total energy. Calculate total energy. And I'll use exactly what we use. So this is exactly the same formula, but I'm just going to multiply each with the energy it contributes. So now I'm trying to calculate, if you want average energy, or like, let me write it like E. And each one is going to contribute like h nu. And now is the integral that I need to take. And this one is going to be equal to, 8 pi over c cube. There's volume, and I am summing over from 0 to infinity. The nu and nu squared 1 over e to the h nu over kt minus 1. And this is h nu. So I'll do the same thing. So I'll multiply this with h nu over kt, h nu over kt squared. There's already h here, so I'm just going to divide this by kt. And what I need to do is like kt 1, 2, 3, 4 divided by h cube, because I didn't multiply this one with h. So this is h cube. And the total energy comes out to be 8 pi over c cube volume k t to the 4th divided by h cube, and this integral from 0 to infinity du. Now this is the previous one was u squared, this is u cube e to the u minus 1. Again, if you put this in Mathematica and calculate this, it also gives you the result in no time, and the result is like what? Pi to the 4 divided by 15. And the result is, let me just copy this. Pi to the 4th over 15, right? So then what we find is like this average energy per unit volume is going to be proportional to t to the 4th, right? It's not only finite, right? We found the average total energy, but also it is changing with as a function of temperature, with the 4th power of temperature. And this one, there is like a constant. Here's the exercise. Actually, it's not an exercise. Just write these constants and pull it out. This is called Stefan-Boltzmann law. And one last thing, maybe after that I can finish it. We can also, like, okay, so this was the Blackbody radiation. So this is u of nu, and this is nu, and there is like something like that. There is like some nu max, right? So you can also calculate that. Let me write it in a brief way and summarize it for you to do it, but you can just calculate for yourself. So this u of nu is going to be, let me use some new variable z. So this is going to be z cube e to the z. It is not exactly, but it is proportional to z minus 1, where z is equal to h nu over kt. And how do I find the peak? If you want, I am trying to find z max, and if I can find z max, I can find nu max. How do I find that from this function? So, right, you take the derivative and set it to 0. So to find z max, I'm just going to do du dz, which is equal to 3 z square divided by e to the z minus 1. Did I get it right? Yes, that's right. Minus z cube divided by e to the z minus 1 squared e to the z, and I set it to 0. Now this one is going to cancel this one, and I have an equation. Okay, this z square is going to cancel this z cube, and I have something like this: e to the z minus 1 is equal to 1/3 z e to the z. Did I get it right? E to du minus 1, 1/3, yes. And yeah, you can find, for example, this graphically, just plot this side and this side and find the intersection. And graphically, I found this to be around Z max around 2.8. And that says like H nu over KT at maximum is about 2 point, like let's say some constant. Or you can just convert this to wavelength, right? This is going to be C is equal to lambda times nu, right? And from here I can just like say 1 over T times lambda max is constant, or I can just say T times lambda max is some constant. You can calculate what this is, and this is called I think Wien's displacement law. So this is Wien's displacement law. What this says is like you look at the spectrum of anything, and from the peak of the spectrum, the most wavelengths that comes to you is determined by the temperature. If you increase the temperature, you can just shift it to the right, or if you decrease the temperature, you can shift it to the left. Okay, any questions or comments? Okay, maybe then we can finish it today and continue on Monday. Okay.